Hi, so welcome to another exciting installment of Advanced Computer Architecture. What I'm going to do in today's video is introduce a classroom discussion. The classroom discussion's topic is what I call the Turing Tax, and what I'll do towards the end of this short video is introduce what I mean by that. But along the way, we'll cover a number of interesting topics which I think will feed into our thinking about that. So let me introduce this guy, Presper Eckert. Presper Eckert was one of the inventors of a landmark computer in the very early days of computing, a thing called the ENIAC. ENIAC was designed during the Second World War, primarily for military purposes. It wasn't actually operational until shortly after the Second World War, but it was subsequently used for various things as part of kind of Cold War and so on. It was enormous, apparently 27 tons. What we're looking at here is a picture of the room in which it was built. And in those days, computer architecture was done on a scale kind of similar to the architecture of at least rooms, if not actually buildings. It's huge. Let me just show you. This is Mr. Eckert. Incidentally, this guy he looks a bit like the guy who's found the remote. That's because he has. This remote control, you can plug it into various units around the machine. And what you can then do is debug with it, because it's got a number of buttons on it to control single stepping of the machine. So he's single stepping through a configuration of the machine to see what's wrong by watching the flashing lights. Let's have a look at what these various things are all the way around. The way to see that is to look at the architecture of this room, and here it is. So at the back of the room, which is over here, we see 3 multipliers and then a bunch of accumulators over here. In fact, there are a couple more accumulators over here and a couple more over here. We also see over here a couple of square root units and so on. A divider. So this is a machine with many functional units, and potentially those functional units could operate in parallel, and we'll see a bit more of that in a moment. So how do you program this thing? Well, here is a small extract, a little image of a snapshot of a larger document actually, showing how you program it. And what this is a wiring diagram. It tells you how to wire the machine up for a particular computation. So in those days, programmers didn't write code, they drew diagrams like this one. Here they are actually programming it. They're presumably, it's a little hard to tell what they're really doing, but my guess is that this is the document we were just looking at. And what they're doing is making sure the machine is actually plugged together in the right way for that particular program. Here's some more of that. The reason why I thought I'd show you this is, well, I'm leading on to a couple of things, but along the way I thought I'd show you one of my favourite quotes from Presper Eckert. And it goes like this. So this document, incidentally, is from the first international, it's not so much a conference as a summer school actually, it was 6 weeks in 1946. When all the world's, or the Western world's, computer experts got together to share their experience, much of it gained during wartime projects. And what he said was, "Again, I wish to reiterate the point that all the arguments for parallel operation are only valid provided one applies them to the steps which the built-in or wired-in programming of the machine operates. Any steps which are programmed by the operator, who sets up the machine, should be set up only in a serial fashion. It has been shown time and time again, over and over again, that any departure from this procedure results in a system which is much too complicated to use." 1946, over and over again, they had done parallel computing, they had decided it was hard. Of course, this course is going to be substantially about the effective exploitation of parallelism. And one particular thing that we will look at repeatedly is to what extent is the parallelism automatically extracted from a purely sequential instruction set versus actually exposed explicitly in the binary assembly code of the program. So does the assembly code represent the parallelism in the program? And also, of course, we'll look at higher levels of parallelism like threads and multi-core and clustered systems and so on. So the other thing that ENIAC is really famous for is its part in the story of stored program mode, or the fetch execute idea. So what they did late in the lifetime of the ENIAC machine was they actually configured it to be a stored program computer, meaning that they found a way to plug the units together to build a machine that could fetch instructions from memory, decode them and execute them and go round again. And then they didn't have to rewire it ever again because they could just change the code in its memory. So that idea is dated. There's a famous article by Donald Knuth here to 1945, and in particular Knuth evidences this manuscript from John von Neumann. John von Neumann, we'll see in a moment, was a very famous mathematician with his finger in a lot of different things. But here he is, and I'll try and read it for you because it's not so easy to read the handwriting. We now formulate a set of instructions to effect this four-way decision between alpha and delta. We state again the contents of the short tanks already assigned. Now, what he means by tanks here are memory units. So the ENIAC didn't have RAM like we know it today, and instead data was stored in mercury delay tanks. And we don't have time to go into how they worked, but that's what he means by tanks in this manuscript. So then he goes on, now let the instructions occupy the long tank words 1, 2, ... And he goes on to talk about the different instructions that might be represented. So he's clearly describing a fetch execute machine of some kind, a programmable machine. Turns out that although it is true that von Neumann wrote that manuscript in 1945, the machine was not actually configured to fetch and execute instructions. The first machine to actually run a stored program is a machine in Manchester in the UK, and it was in 1948, June 1948. And this is the first program to ever execute. So it's a landmark in the history of computing. So this manuscript is dated July 1948. Apparently, an earlier version of this code, this is an amended version of the code, apparently this ran in June 1948. And the title is Kilburn Highest Factor Routine. And, well, I'm not going to pretend that I know what this means. This is a subtract, stop. Yeah, don't know. Here's some binary coding. Binary programming was at a pretty low level in those days. Here is the machine that it actually ran on. It's called the Baby, or the Manchester Small Scale Experimental Machine. Actually, although that machine is no longer in existence, it's been rebuilt. And if you go to the National Museum of Science and Industry in Manchester today, you can actually see this reconstructed version of the same machine. So if we just compare them, that's the old one, this is the new one. They're very similar, but this one actually works, or at least it worked at the launch of the machine at the 60th anniversary of the Baby. So I mentioned John von Neumann, and here is his mugshot. Von Neumann is well worth looking up. He's a significant figure in the history of 20th century science, mathematics, and to some extent politics. He was a huge player, for example, in the development of the hydrogen bomb. But he has his name on this stored program von Neumann concept. And the reason what I'm doing here, I want to introduce this guy. So this guy has a very special place in my heart because he's one of the pioneers of compilers. He's not the first compiler engineer. It's probably Grace Hopper. But John Backus led a project at IBM to build a compiler for a new language called Fortran. Fortran stood at the time for formula translation. And the idea of formula translation was that we would put all the programmers out of work because we would just get the mathematicians to code up the formulae directly, and then they could be translated by the machine into the instructions necessary to execute them. As you might have noticed, turns out compilers and programming languages didn't put programmers out of work, and you might wonder why. But for his work on compilers, John Backus was awarded the Turing Award, the Nobel Prize for Computer Science, you might say, in 1979. You might recall, incidentally, when I introduced our textbook authors, they were also winners of the ACM Turing Award considerably later. When you win this Turing Award, you are invited by the ACM to give a lecture on a topic of your choosing. And a number of fascinating topics have been chosen by Turing Award lecturers over the years. His was a particularly interesting one because he coined this term, the von Neumann Bottleneck. And what he was doing was he was trying to emphasize that when you program a von Neumann machine, what you are doing is enforcing a one instruction at a time programming model, and you are committing in the code to the specific order in which those instructions will be executed. So he kind of argues that the von Neumann bottleneck is not just a hardware problem, it's actually a conceptual barrier, because what it does is it confuses programming with scheduling. What you are forced to do when you program a von Neumann machine is explicitly schedule the computation. And he wanted to argue in his lecture that actually we should try and program in a way that expresses the data dependencies in our programs without prematurely committing to exactly what order the instructions should be in. What he was doing was arguing for functional programming. Functional programming does just that. You don't specify the loads and stores that go on during the execution. You don't specify the order of evaluation. You describe the dependencies in the program, and then the compiler and the runtime system figures it out. And what we might hope, if we could raise the level of abstraction in programming, is to get not only the flexibility and ease of programming that we might hope from functional programming, and from freeing ourselves from this commitment, this necessity to overschedule, but we might also get performance from parallelism, because we can parallelize in a way that doesn't involve unpicking the scheduling the programmer did. So, where this is going, back to the very title of today's session, is how to beat the Turing tax. And we should move on to Mr. Turing. Here is Alan Turing's Google Scholar page. Most Google Scholar pages are for living and publishing authors. Most people don't publish that many papers in their lifetime. Turing didn't publish that many, but they have been incredibly successful and impactful. He made huge contributions. I'm sure you've all heard of him. He made huge contributions in AI, not just the imitation game, which led to the title of the film, but also in thinking about what the power of future computer architectures could do to our potential for building apparently intelligent machines. Also, particularly nice, I think, is that he, quite independently of any of the computer science he did, also made contributions in morphogenesis. Which is the mathematics of how animals get their shapes, and perhaps particularly of interest to him was how the patterns on animals' skins get their patterns. That work, incidentally, is coming back. But even when he wrote it, it was quite influential. The reason we're here is actually to talk about this paper, these two papers. Along the way, I might also point out that not all of Turing's work was academic. He is also famous for playing a significant part in the winning of World War II, of the defeat of fascism and Nazi Germany. And I'm sure you've all heard this story before, but this is the Enigma machine. This is a document from the Luftwaffen Maschinenschlüssel. It's an Air Force coding machine key document. This here says, Achtung, watch out, do not let this fall into enemy hands, because these are the keys for the future messages. And this machine was designed by Turing and others to decrypt messages encoded on this machine using keys from such a document. And it was success in doing so that played a significant part in various military advantages that potentially, arguably, led to the outcome of World War II. I promised that we'd get to the Turing Tax. All right, one more distraction. There's a lovely book in the library of a collection of Turing's papers on morphogenesis, on the development of biological shapes. And in the frontispiece, in the introduction of that book, is this picture. This picture is of Alan Turing by Alan Turing's mother. Alan Turing went to a traditional British public school, and at such schools, the boys were forced to participate in sports. Some of them, as you can see over here, participated with some enthusiasm in games like hockey. Others, like Turing, were unmotivated by sport and more interested in looking at the daisies and how they get their shapes. This is the paper that introduces the Turing Tax for me. It's Turing's original paper on computability, on trying to characterize what is computable and what is not. And the problem, of course, is that what's computable is hard to get your head around because it involves what's computable by all the machines you could possibly build. All the machines you could possibly build is a pretty difficult thing to include in a proof. So he came up with a trick. He designed a universal computing machine that could do anything that any particular machine could do. All you have to do is program it. So this, 1936, predates the manuscript from John von Neumann, predates any attempt to actually implement a stored program machine. But in this paper, and I've skipped to the relevant section 6, in this paper he says, it is possible to invent a single machine which can be used to compute any computable sequence. If this machine is supplied with a tape on which the beginning is written the description of some computing machine, then it will compute the same sequence as the machine being described, right? That is the universal concept. That's the stored program concept. And he proceeds in this paper to give a concrete example, just to prove that it really can be done, of a universal Turing machine. Here is a universal Turing machine. It's actually a slightly later one from 1952. And it's published in 1952 by this guy Moore because it's a bit smaller and simpler than Turing's original one. It's only a 15-state machine. So it's not really a very complicated device. I won't go through this one, not least because I don't quite understand how the diagram works. But instead, let's get to the Turing Tax. So Turing realized we could use digital technology to implement any computable function. And he proposed this universal computing device, a single machine that with the right program can do anything any computer could do without further configuration. The Turing Tax is a term for the overhead of universality in this sense. And you can count the overhead in terms of the execution time or the manufacturing cost of the machine or the total amount of energy required for the computation. It doesn't really matter how you count the cost. What we're trying to do is to characterize the cost difference between programming a general purpose machine to do the job versus designing a finely honed application-specific device to do the job. And for me, this is the essence of computer architecture. It's also kind of the essence of the difference between electrical engineering and computer science. In computer science, we kind of start from the assumption that we're programming general purpose machines. In electrical engineering, we might be more interested in designing special purpose machines. What we want to do is to beat those electrical engineers and design general purpose machines that get really close to the potential performance of a specialized device. Let me show you an example. Pong. I wonder if you've ever seen this. So Pong is an exciting computer game. It was exciting at the time. People thought this was really cool. You could probably not reasonably afford to buy your own machine to play Pong, but you might easily go to an arcade or to even a pub or something and find a machine, put your money in the slot and have a game of Pong with your friends. So clearly there must be some kind of computer inside this box. This is the computer that was inside the box. It was designed by Atari. This is the original document from, this particular one's from 1974, but the machine was actually launched before then. One of the reasons I'm showing you this particular diagram is to show you how simple this thing is. So in the middle here we can see individual transistors, individual gates here. There are some small integrated circuits in this picture. So for example, this one here is a 7490. A 7490 is a decade counter. It's a counter for counting up to 10 and then round again. So if you want to put a score on the screen or something, you need to count up in tens. There are various other similar things. None of these chips have more than a dozen or so transistors in. There are about 75 chips in the machine as a whole. So there's probably less than 1,000 transistors, potentially considerably fewer, to implement that game, right? Now the trouble is, of course, that that circuit is no good for any other games. It only does Pong. At the time, back in the very early 70s, you kind of could have found a general purpose machine to do this. You could have programmed a large-scale computer. Turns out, coincidentally, that 1971 was the launch time for the very first commercially available microprocessor, single-chip processor. So conceivably, you could have used this chip, the Intel 4004, to build a programmable implementation of Pong. This is the block diagram. So we see a machine that fetches and decodes instructions, issues control logic to an arithmetic unit here, some accumulators, some I/O, program counter, stack, and so on. Let's have a look at the circuit diagram, because we were comparing circuit diagrams. The Intel 4004 processor had 2,300 transistors. Every one of them is actually drawn on this picture. I wonder if I can scale this up a bit to show you. These are individual transistors that we're seeing here. So a slightly more complicated device could potentially have been programmed to implement Pong at roughly the same time. Incidentally, because it's interesting, let's look at a die photograph of the 4004 processor. So each of the colors here refers to a different layer in the photographic, each layer of the masks used to manufacture this chip. And so each of the transistors that we saw in the circuit diagram is actually directly implemented by drawing the mask that will construct the field effect transistor on the surface of the silicon. That was an ancient history example. Let me show you a slightly more modern one. Well, the next couple of slides come from an analysis in a paper in 2010. This table comes from the paper cited on the next slide, and the pictures come from the citation here. The starting point is this. Let's look at H.264 video encoding. So this is a very, very popular, very successful video encoding tool. And of course, it's important to be able to do this in real time and to achieve very high levels of compression. And Intel made it a priority that you could run H.264 on their CPUs. At that time, we're talking about the Intel Pentium 4 CPU. And they produced hand-coded libraries to do rather low resolution, real-time, 30 frames a second, on a Pentium 4 with this chip area. And it meets the performance objective of 30 frames a second. If you want to run it at a higher frame rate, it works, but it doesn't actually meet a reasonable frame rate if you want to run it at a higher image resolution, then you can't meet the target frame rate on a Pentium 4 processor. Meanwhile, the chip whose design is described here, roughly contemporary as described in this article, implements the same computation at 30 frames a second at full HD resolution on a smaller device with much, much less energy per frame. How did they do it? Well, this machine is really not a programmable machine. Actually, thinking about it, I should probably flip to the next slide to try and explain this. So H.264 works in essentially 5 stages, and it works by applying these 5 stages to a stream of macro blocks. So you take the image and you divide it up into blocks. And each of these blocks has to go through the integer motion estimation. So you're trying to guess how this block has moved relative to this patch of the image in the previous frame. Fractional motion estimation is where you refine that estimate. And the remaining steps essentially correspond to finding a compact encoding of that information. So the machine consists of IME, FME, and then these 2 stages in a pipeline. And over here, we see IME, FME, and the 2 remaining stages in a fully specialized computer architecture, a non-general purpose computer architecture. Inside this IME box, we have this picture, which involves an array of 8 of these sum of absolute differences trees, SAD tree structures. And down here, we see what a SAD tree structure is. This FME engine is elaborated in more detail here as an array, again, of 4x4 blocks of this design. Not quite sure what they're doing. This, I think, is... no, I don't quite know what this is doing. But what I'm getting at is that this thing is kind of fully customized all the way down to the finest details for this particular task. What this article along here tries to do is to attribute the performance difference between the CPU implementation, so if we look at execution time here, or frame rate I should say, the CPU implementation, as you successively customize the different stages of the pipeline, you get improved throughput. So they took a simple RISC processor, they added some parallel instructions to it, and we will look in detail later in this course at SIMD and VLIW instructions. Then some fusion tricks, and they're described in the article. Some magic instructions, so these are special instructions to compute particular complex terms involved in the encryption, in the compression algorithm. And each of these steps takes us closer towards the performance that you see in the ASIC design. So what are we doing here? We're looking at an attempt to measure the Turing tax, the performance difference in time over here and energy over here of a fully software implementation on a general purpose computer versus a fully customized implementation. And along this pathway here, we get to slightly more specialized hardware. Okay, so that's the Turing tax idea. Let's take it back and relate it to what we've been learning at the beginning of this course. So here is the 5-stage fetch execute machine pipeline that I introduced in the pipelining video. Where's the Turing tax? Where in this picture are we paying Turing tax? Where? Well, there are kind of obvious things, right? Like, we shouldn't have to fetch and decode instructions in a specialized machine. Probably. So this part of the machine, the fetch execute part of the machine, is presumably unnecessary. The program counter is unnecessary. The instruction memory is unnecessary. The decode block is presumably not needed, though we would need some kind of sequencing or something, I suppose, to control our special purpose machine. Also, these multiplexers here are being used to select where the operands for the arithmetic unit come from in each cycle, and they're configured, they're controlled by the decode unit for each successive instruction. So we might or might not actually need each particular combination. So there's some Turing tax hiding in there. So we have Turing tax associated with storing instructions, fetching them, decoding them, maintaining the program counter. Branches look like Turing tax to me. Once we start branch prediction, we're really in the realm of potentially avoidable architectural overheads. There's more, I think. So when we talked about hazards and stalls and forwarding, all of that is being configured by the fetch, the instruction decode mechanism. And what we're essentially doing, I tried to show this to you when we talked about pipelining with multiple functional units. I tried to show you the idea that what forwarding does is it configures a data flow graph in the forwarding wires to represent what you've discovered from the sequence of instructions that the programmer has given you. And that decoding shouldn't be necessary in a ASIC design, in a specialized design. Not all the forwarding paths will be needed. Not all the multiplexers to switch them will be needed. And we might even think about co-locating a functional unit that computes something with the functional unit that consumes that result. Registers. What we use registers for in programs is not just as a place to store things, but in fact as a way to pass values from one instruction to the next. That's actually an important idea. We will see this in a big way in a couple of lectures' time, where registers are truly used to describe the data flow of the program rather than to actually manage the storage of intermediate temporaries. But every time a register is used, we have to do a lookup into a register file. And that, if we knew what the data flow graph was, we could just wire them together. The arithmetic unit is configurable as well. So in the pipeline that I showed you, there's one arithmetic unit and it can be configured to do different things, add, subtract, perhaps even multiply in each successive instruction. In a fully specialized design, we might have several arithmetic units, but each one of them can be specialized to the particular operation required in its context. So this brings us to the end, and it brings us to the questions that I have for you. What can we do to avoid Turing Tax? What architectural strategies can you think of that will help us reduce the interpretive overhead of the fetch-execute machine? That's my question. I'm not going to tell you the answers. In fact, I have follow-up questions. Caches. We've learned a bit about caches. They seem important to getting performance, but are they not also a kind of Turing tax? Could we get rid of caches in a specialized device and do something more efficient? So, come to my class next time, ready and prepared to answer that question, to discuss your answer to the question. Next up, and the last slide actually, I've presented you this Turing tax argument, and I've suggested that for some applications like Pong and H.264, you can build a specialized machine, and it might be much smaller and faster and more efficient than a general purpose machine. You could argue, though, that that's something which applies to certain kinds of applications, but that interesting, complicated applications benefit more from programmability. And I would welcome your further thoughts on that topic. Okay. So finally, I have asked you to come to the class prepared to discuss these things. In fact, I would also welcome comments on Piazza. So there's a Piazza bulletin board for this course, and I hope that through it we will have a developing and continuing lively debate around topics spinning out of the lectures that I give you, but also, of course, identifying questions and areas where I have been unclear or where you haven't quite understood what I've been saying. So with that, I'll finish, but I do expect you to have done a bit of thinking and homework, maybe even made a note to yourself about what you might say. Thank you very much. Till then, see you soon.